Hello, let's do acid-base titrations and how they fit in with stoichiometry. Acid-base titrations, they are based around neutralization reactions, and they're a very important process or mechanism of working out concentrations of substances, and they are a pillar of chemistry. In chemistry, you need to be able to do titrations, understand them, and be able to do them well. And in fact, some chemists spend most of their lives doing little else but titrations, even though there's sometimes machines that will do it for you. But even those machines rely on accurate titrations being done by a skilled chemist to calibrate them. Now, they are a type of volumetric analysis where the unknown concentration of a solution is determined by reacting it with a solution of known concentration, and an indicator is used to indicate when a reaction has taken place. And so they very much rely on stoichiometry to have their complete analysis of the process. Solutions whose concentrations are known accurately are called standard solutions, and we talked about how they can be made very accurately and how chemists require those for things like titrations. Keep clicking the mouse. Now, we've got a whole lot of words to go through here. The standard solution, so the solution that you know the concentration of, is placed in a burette, which is used to deliver a definite but variable volumes of liquid. It's like an upside down measuring cylinder, or a measuring cylinder with a tap. Looks like this. So it has a 0 up here, and then in this case it contains 50 milliliters, and then it has a little tap, and so you fill this up with your standard solution. In a titration, the volume of the liquid measured in the burette is called the titrate. So this would be how much you use is the titrate. The solution of unknown concentration is added to a conical flask using a pipette. Do we know what a pipette is? Well, that's a conical flask. We've used these before, and these are specifically designed for titrations to avoid splashing. Because you have a liquid down here, you're adding drops, and the drops will splash up onto the side and you can wash them down easily. Now, this is a pipette, which is usually they have a mark on them, and they come in different sizes depending on what volume you want to measure. This is a 20 milliliter pipette, and it's been calibrated to very accurately measure out 20 milliliters, much more accurate than using a measuring cylinder even. And the pipette is used to deliver a known volume of your liquid which you don't know the concentration for, and that volume is called an aliquot. So in this case it's 20 milliliters. A suitable indicator is also put in the conical flask, so you have in here your unknown plus an indicator, because this is usually an acid or a base depending on what you're using. And the solution in the burette is slowly added to the aliquot until the color changes, or the indicator changes color. And this process is actually the titration process. So some of you may have done this. I'm going to go through a little animation shortly, and then when we actually do the prac, you'll get a chance to do it as well. I keep clicking and nothing's happening. At the point at which chemically equivalent amounts of acid and base, according to the equation that controls it, are present, that's called the equivalence point, or equivalence point. There's another way of pronouncing it. That point is at which the indicator changes color is called the end point, and is usually about 1 drop after the equivalence point. So you have to be measuring out this using the tap to an accuracy of within 1 drop, and it takes a bit of practice and a bit of skill. Titrates within 0.5 milliliters of each other are called concordant titrates. That means they're good. If you outside of that, that's more than 1 droplet, you'll usually have to do it again. And if you're doing it professionally, you'd end up doing a lot until you get it very accurate. 3 concordant titrates are needed to calculate the average. And this is what you look like. There's the tap dripping in. Actually, this nozzle should be down a little bit, perhaps. This person's holding it up to swirl it. They look very serious because this is a very serious process. It's one of the fundamentals of being a good chemist, is being able to titrate. Now, try this refers to this. Let's drag this across, and this will be available on the OneNote. Let's just make sure you can see that. And what we've got, we're going to go through a step-by-step guide of using a titration with a burette and a pipette. So the first step is, I'll read it out for you. Fill the burette with the acid up to near the 0 mark using a funnel. Then remove the funnel. Okay, come on, let's go. Let's go. Here we go. So there we are, put a funnel in there, pour it in, careful not to slop it around, and up close to 0. It doesn't have to be accurately to the 0 because you're actually going to record that measurement. Next one, using a pipette filler, fill the pipette to above the ring and then let out some of the solution until the meniscus just sits on the ring. Next one, deliver 20 milliliters of solution from the pipette into the reaction flask. This amount is termed the aliquot, and that's a conical flask. Whoops, I keep ticking there. Add 3 drops of a suitable acid-base indicator to the base. In the case of methyl orange, it will turn yellow, and we'll be using a different indicator. There's a whole range of indicators to use. Place the reaction flask under the pipette so the bottom tip is just inside the mouth of the flask, as I pointed out earlier. Take the initial burette reading, correct to 2 decimal places. This might be 0.25 milliliters, and record it, obviously. Here we go. Start adding the acid from the burette into the base in a steady stream, stirring constantly. When nearing the end point, the indicator will show its colour in an acid when the acid has dropped into solution when you swirl the flask. However, the colour will disappear. The closer you are to the end point, the longer it will take to disappear. With a methyl orange indicator, it will be yellow because there is an excess of base, but it will turn red when the acid drops down into the base. When the flask is swirled, the red disappears and we will just see yellow. This is the signal to start adding the acid from the pipette drop by drop instead of a steady stream. Okay, so now we zoom in and we're adding it at one point of this drop by drop addition, say at 21.25 milliliters. The indicator will turn yellow to bright orange. There it goes. The orange colour will not disappear on swirling. This is called the endpoint. Take the final burette reading, which is say 21.25 milliliters. Note this means the flask will still be less than half full, which is good. Any further additions of acid to the mixture will turn the solution red, and we've gone too far. Record the titrate, the final burette reading minus the initial burette reading. In our example, that's 20.94. Okay, and that's how you do it. And so we'll be doing a prac on that. Let's get rid of that. And this is the step-by-step process of how you do it. I'll be giving you a sheet of this hopefully, and it will be on your OneNote. So if you can't read that, I'll give you a better version of it. But basically, it's what we're doing. Now, what does it mean? What do we get? Well, we get these sorts of numbers. And this is an example, and we'll go through 1 or 2 examples. 1.33 grams of anhydrous sodium carbonate is placed in a 250 milliliter volumetric flask, and water is added to the required mark. So that's our known solution. This standard solution is placed in the burette and titrated against a solution of hydrochloric acid, whose accurate concentration is to be determined. That's our unknown. It was found that a 20 milliliter aliquot of HCl, so that's our volume of our unknown, required a sodium carbonate titrate of 23.5 milliliters for a complete neutralization. Calculate the concentration of the sand solution and the hydrochloric solution. So in this case, the burette has actually got a base in it, because we are using a known base to work out an unknown acid. Now, first step is work out the concentration of our standard solution. So we've got our mass divided by the molar mass gives us our number of moles. Then we work out we have to work out the concentration by looking at the volume. So we end up with 0.062 moles per litre. So that's the concentration. We've done that before. Now, B, write the equation for the reaction. This is where the stoichiometry comes in. So we write the equation. Okay, we've got this. We've got the number of moles of sodium carbonate, and we've got the volume used, because that's our titration. And so we can work out how many moles that represents. Now, our moles of hydrochloric acid will be 2 times that. Now, where does that 2 come from? Well, the ratio 1:2. So they're not strictly following the stoichiometric steps. We might actually go through those steps. Do I go through them shortly? I might actually go through them. And so they work out how many moles of your unknown you have, and then using the concentration formula, where you know the number of moles, you know the volume used, because that's how much we poured from the pipette, we can work out the concentration. Therefore, the hydrochloric acid has a molarity of this. Right. Come on, pause. Don't want to pause. Okay. Alright, so let's pull up a screen. Let's make it a black screen so I can write on it. And let's write on it in yellow. The poor old thing. So let's do it in the stoichiometric way of doing it. So first off, we write our equation. Na2CO3 plus 2HCl goes to 2 NaCl plus, I'm just copying this from what was given before, but that's okay. So there's our equation, and this is our known, and this will be our unknown. So how do we go about it? First of all, what do we know about the known? We know C equals 0.062 moles per litre, and the volume required was 0.0235. That's a 3. Okay. Therefore, we need to convert this to moles, don't we? Okay, N equals CV we're going to use, and that is going to give us a value of 0.00146 mole. Let's change colour now to let's go red. Hopefully that shows up alright. Now that we've got this, we now use the molar ratio. In this case, it's 1:2, and that would tell us that we therefore need 2 times this amount of moles. That means that N for our unknown is 0.00291 mole. Now we need to convert that into the concentration. What do we know about that? Well, we know we're going to use C on V, and we know that the number of moles is 0.00291, and our volume of unknown was our burette, our pipette, which was 20 millilitres, which is 0.02 of a litre. Therefore, our concentration equals 0.146 moles per litre to the minus 1. And so that's the way that we've done it in stoichiometry before. And I don't mind if you do it either way, but if you set it out like this, an examiner or marker or yourself can check everything and see what's happening, and also pick any mistakes that you have made. Alright, so hopefully we can do that. A little bit long-winded, but that's the way it is when we're learning something new. Now let's see if I can actually get this. Let's go to slide. No, let's get rid of the screen. Unblack screen. There we go. Let's move on. Now, a couple of examples for you to do, so have a go at them. You get a feel for them after a couple of goes, and there's some at the end of the chapter as well for you to do. And speaking of the end of the chapter, you're now here. Do the multiple choice questions and do these review questions, and then theoretically that's the end of everything you need to know in physical science. Yay! See you later.